In this lecture, we want to discuss the solution of some examples regarding the elasticity chapter. In this example, we have a steel wire that has length 5 meters length, 5 multiplied 10 to the power negative 6 meters squared. This is the cross-sectional area of the wire. It's given its proportional limit stress. Proportional limit stress is the last point of proportionality between stress and strain. It's also given the breakdown stress, which is the stress which causes the breakdown of the wire. If this wire is fixed vertically, it's fixed to the ceiling, and EST equals 19.5 10 to the power 10 Newton per meter squared. E means Young's modulus of the steel. Young's modulus of the steel. Elasticity, longitudinal elasticity modulus. It's required to calculate the maximum load that this wire can carry before exceeding the proportional limit. When asking for the maximum load, this means the maximum force that this wire can hold or the maximum mass it can hold. Then we want the maximum elastic elongation of the wire and the maximum loading before breakdown. We can draw a small figure for explaining the example and put the givens on this figure as shown in this screen. If I want to calculate the force is the stress multiplied by the area. Which stress I use? The first question was maximum load before exceeding the proportional limit. So he needs the proportional stress and to calculate the force from the proportional stress. That's why we will substitute with the proportional stress 3.6 multiplied by 10 to the power 8. We will multiply the stress with the area to find the force in Newton. If it's required the maximum mass, it's also loading. We know that force equals mg. That's why m equals F over g. The second required was the maximum elastic elongation. It wants delta L maximum. Delta L maximum is when using the force maximum or the T proportional. We put the law T proportional equals Young's modulus multiplied by the strain. The strain is delta L over L. Put delta L in the left side of the equation. In the other side, you will have T proportional multiplied by L over E. Substitute with the given T proportional, L is 5 meters, and Young's modulus. You will find the delta L, which is the elongation happened in the wire. As for the third required, it wants the maximum loading again, but before it breakdown or rupture of the rod. So now we will use the breakdown stress, which is greater than the proportional stress. So do the same, but using the breakdown stress. If you want to get the force, multiply stress by the area to get the force. If you want to get the mass, divide this force by G, you will get the mass in kilograms. This was discussing example 1 that we did in the lecture according to the chapter 2 of the elasticity. Example 2, in this problem, we have a copper rod connected to another steel one. So now we have two rods. The length of the copper rod is giving 2 meters. and it's given also its cross-sectional area. As for the steel one, its length is L. L is unknown. We don't know the length of the steel rod. And its area is half that of copper. Is half that of copper. We have the area of copper, so we have the area of steel half its value. When the system is subjected to an external tensile force, this is the force that is applied on the system, the extensions in both rods are equal. This is the condition that is stated in the problem, that equal extensions in both rods. So I write it into an equation, delta L copper equals delta L steel. Extension is delta. E for steel is given and E for copper is given. This is Young's modulus for steel and this is Young's modulus for copper. It's required to find the length of the steel rod. We noted before that the length of the steel rod is unknown. We want to find it. The second required is the strain in each rod. We want the strain in the steel rod and we want the strain in the copper rod. Again, we will draw a sketch or a simplified figure for this problem. So we draw a copper rod connected to a steel rod and we apply the external force for sure, as we discussed in the lecture. It's from both sides. These are two forces. Then we put all the givens on the sketch. We have the length of the copper. We don't have the length of the steel rod. Area of the steel is half area of the copper. And we start solving. We will start solving by the condition givens. It's given that same extensions, so delta L copper equals delta L steel. I will replace delta L with other values. From where? From this equation. T equals Young's modulus, strain. This is the only relation I know concerning the strain and the stress. But instead of the stress, I can write F divided by the perpendicular area. And instead of the strain, I can write delta L over L, which is the initial length. Now I want delta L in terms of the other quantities. So delta L equals FL divided by EA. Instead of delta L, write FL over EA. It's the same law, but different form. And in the other side, write FL over EA. This is for steel and this is for copper and steel. You know E for copper and you know E for steel. Also, you know area of the copper and area of the steel, which is half the area of the copper. Length of the steel is given in the problem. L of the steel is unknown. This is what I'm searching in this equation. And for the copper and rod steel, it is the same axial force. Note that we have the same axial force applied on both rods because they are connected on the same axis. That's why we can get rid of F in both sides. The only unknown in this equation is the length of the steel rod. You can substitute with the givens and calculate the length of the steel rod. The second required was the strain in each rod. From here, we have the strain equals the stress over the strain equals the stress divided by divided by Young's modulus. So calculate the stress in the copper, force over area, and then calculate the strain. Similarly, you can do the same with the strain of steel. Don't forget that it's given the value of force. So I will take the value of the force divided with the area of the copper. This will give me the stress applied on the copper rod. From the stress and Young's modulus, I can calculate the strain of the copper. Same steps could be applied to get the strain of the steel. Let's see another example. This example states that in an elevator or a lift, steel cable is used. This is an elevator, and this is a steel cable connected to the ceiling and carries the mass of the elevator. This radius of the cable is given, so I know the area of the cable. If I have the radius of the cable 1.5 centimeters, so the area of this steel cable is pi area of any circle. The cross-section area of the cable is a circle, is pi r squared. But take care, we are using SI units, so the centimeter is divided by 100 to be in meters, so as to have the area in meters squared. This steel cable supports a maximum load of 1000 kilograms. This is the maximum load that this steel cable can carry or can support. If the strain in the cable must not exceed 0.01%, this is the strain, the maximum strain. But again, take care, we are not dealing with the strain as a percent. We are dealing with it as a fraction. So 0.01 is divided with 100 to get rid of the percentage. And this is the maximum strain that this steel cable can carry. Find the maximum acceleration of the lift when it moves upward. It's required to get this acceleration. For sure, this lift is going up and down, up and down. Now I will imagine it's going up and I will calculate its acceleration. It's also given the Young's modulus of steel equals this value, and the g is the acceleration of gravity is 9.8 meter per second squared, as we are used to substitute with it this value. Young's modulus in our equation is E capital. Let's start solving this equation. In this, in this problem, there is movement. So from Newton's law, sigma forces equals mass multiplied by acceleration. I want to sum the forces. So I'm taking the positive direction upward with the acceleration. In this direction, we have F. It is the tension force in the cable. And in the other direction, we have mg, which is the weight of the elevator. That's why signal forces, we have F, the tension force in the steel cable, minus mg, because it's in the opposite side, equals m multiplied. This is from Newton's law, sigma forces equals mass multiplied by acceleration. It's required to calculate the acceleration. It's required to find the maximum acceleration of the lift. I will put the acceleration in the left side of the equation. In the right side, I will find F minus mg divided by m. But this F is the mechanical force acting on the tensile force in acting on the steel cable. I can find F in terms of Young's modulus strain, and area. Again, we don't have except this relation. Stress equals Young's modulus multiplied by the strain. Remove the stress and put force divided by area equals Young's modulus multiplied by strain. So force equals Young's modulus strain multiplied by L area. Substitute by the force E epsilon A divided by M minus mg over m, which is g. Then you substitute with all the givens. You try to make this exercise and use your calculator to calculate the acceleration and make sure you will find this final answer. Acceleration is 4.3 meter per second square. This was an example of how to get the acceleration of an elevator moving with acceleration A, but take care of changing your units. Here we cannot use it percent, and here we cannot use the radius with centi. We are dealing with SI units, which deal with meters, not centimeters. The next example, we have a 100 kilograms rock. This rock is 100 kilograms, which makes mg its weight downward, and it's fixed with three cables or three wires, three rods. In this example, he's naming these three rods, one of iron, one of copper, and the third one is also from copper. These three rods initially have the same length. They have L node initially and the same area before loading the 100 kilograms. After we hanged the 100 kilograms, these kilograms are horizontal, kept horizontal, which means that if I start from this point and I start from this point, they have the same initial length, so they start from these 3 points. After loading, the delta L, which happened in the first rod, is the same as the delta L which happened in the second, the same delta L which happened in the third. Why? Because it's mentioned in the problem that it's kept horizontal. It's very important to know that when dealing with horizontal, change and the same initial length, this means that same delta L occurs. With different delta L, this will be inclined like this. If we assume that delta L of steel is not equal to delta L of copper or whatever, it won't be horizontal. So from reading the example correctly, you can understand the givens correctly. It's also given that E for iron is double E for copper. What is E? You remember E is Young's modulus. E stands for Young's modulus. It's required to find the force acting on the iron rod and the force acting on the copper rod. Again, we don't have except of one relation. Stress equals Young's modulus multiplied by the strain. You can remove the stress and put force over area, and you can remove the strain and put delta L over. If you want the force in terms of the other physical quantities, you can write it like this. Okay, let's start solving. We can use the equation of equilibrium. At equilibrium, sigma forces in the y directions equal 0. Sigma forces in the y direction equal 0. You can add the forces in the positive y, it's equal to the forces in the negative y direction. So, from mechanics and our study of the statics, at equilibrium, F1, I named F1, which is in iron, and F2 in copper, F2 and F2. We have in the positive y-axis F1 and also F2 and F2. So I have in the positive y-axis F1 plus 2 F2. In the negative y-axis, I have the weight of this rock, which is mg. We can write easily the equation of forces at equilibrium. At equilibrium, F1 plus F2 equals mg. And from the condition given, remember, it's given that Young's modulus of 1 equals double Young's modulus of 2. I removed Young's modulus and write it in terms of other quantities. And the same for Young's modulus number 2. But the relation between them is double. Okay, what we can simplify from this equation? Same initial length, same area, same elongation, because he said it's horizontal, so same elongation. We can remove all this from the equation, and it is simplified to F1 equals 2 F2. This is equation number 1, and this is equation number 2. We can solve two equations to get F1 and F2 easily. You can solve it and you will find F1 is half mg, F2 equals quarter mg. Of course, you can substitute with m and find the value of F1 and F2 in newtons. Let's have another example on longitudinal elasticity. We have two rods, rod number A and rod number B, hanging a mass. To hang this mass, we put a sheet of neglected weight, and then we, at point C, we hanged the weight or the mass F. This mass has a weight, which is the force acting on these two rods. For the shown figure, area of rod number A is half the area of rod number B. And Young's modulus of rod A equals 3 over 2 Young's modulus of rod B. It's required to calculate x. What is x? It is the distance from A to point of hanging. I want to hang this mass at point C. Calculate x, this distance, if I want same stresses and if I want same strains. Okay, let's start solving and we'll see what we can do in solving this problem. This problem is in equilibrium. We know from our studies in mechanics and especially in equilibrium that sigma moments is 0. I will choose the point C and calculate sigma moments around point C. If I'm in point C, I have one moment from FA like this and another moment from FB like this. In equilibrium, they are equal. So FA multiplied the distance between point C and the rod A is x. FB multiplied this distance. This distance is 1 minus x. 1 minus x. Because it's given the distance between rod A and rod B is 1 meter. This is the equation of moments. This equation is applied because of equilibrium. In case number A, the condition given, same stresses. Same stresses means stress at A equals stress at B. Stress at A is force over area, force over area for the other rod. So force of area 1 in the left hand side equals force in the rod B multiplied A over A. A of rod A over A of rod B. But it's given that the area of rod A is half the area of rod B. So I know this percent. This percent for this fraction is half. So FA equals half FB. This is equation number 2. But also I have equation number 1 of the moments. Check these two equations, equation number 1 and equation number 2. Two equations in two unknowns, FA and FB. You can eliminate FA or FB and you can get X. You can get X from these two equations. X in this case is 2 over 3 meters. So if you hanged this mass at 2 over 3 meters, you will have same stresses in the two. Okay, let's explain the part B. Part B, I want same strains, same strains. So I will begin with the condition of strain at A equals strain at B. And I will write the strain in terms of other terms, F over EA, F over EA. And then I will put FA in the left-hand side of the equation and put all the other terms in the other side. I found that I have the fraction Young's modulus of rod A over Young's modulus of rod B. Remember, it's given in the beginning of the problem. It's given that the fraction of EA over EB is 3 over 2. And also I have the fraction of areas. So I can substitute with EA over EB 3 over 2. EA over AB equals half. So you can get FA equals 3 over 4 FB. This equation is number 2 or 2 dash. Okay, 2 dash. Compare 2 with 2. This is the condition stress, same stresses. This is another condition when same strains. Now you say you solve one equation 2 dash with one equation of moments. We'll solve it together with the equation of 2 dash. Sorry, this equation. You can get X equals 4 over 7 meters. This was another idea of how to solve these problems. Let's see another idea. If the two rods don't have the same initial length, rod A initially starts with 2L node and rod B initially starts with L node. And also we have this sheet is neglected in math. And then we make the same procedure. We hanged at point C mass M. It's given here that Young's modulus of A is double Young's modulus of B and same A. The difference with the other one that it's not the same initial length. Do the same and think the same. First, sigma forces in the positive y, FA zeta FB equals mg. FA plus FB, FA plus FB equals mg from equilibrium. Also, you can write the moment around point C, FB multiplied x equals FA multiplied 1 minus x. And the same horizontal, that's why delta L equals delta L over. You can solve the same steps and try to find the value of FA, FB, and the value of x, it's half meters. It's very easy to do it yourself. Another example, but now it's on thermal strain. We discussed before that if we increased the temperature of any rod, this rod will expand and change in length by delta x. And we asked ourselves what will happen if this rod is put between two rigid walls. This example was discussed in the lecture, but now we can discuss it with given numbers and givens, and we can substitute with numbers. Here it's given the alpha. Do you remember what is alpha? Alpha is the thermal expansion coefficient. Young's modulus of steel is given. It's given the radius of the rod, and the temperature is increased by 80 degrees. It's required to calculate the stress acting or developed in the rod. Let's do it together. What we know that this rod is put between two rigid walls. If you put this rod between two rigid walls, you know that it can't increase or decrease its length. So I start by putting delta L total equals 0. This rod cannot change length, so change in length is 0. This change in length is two parts. First part is mechanical and the other part is thermal. The thermal part is L alpha delta theta, and the mechanical part is FL over EA. If you add these two together, this will be 0. We discussed if we increase in length due to temperature increase, there will be decrease in length due to mechanical compressive force. Put the force in the left-hand side of the equation, you will find it negative EA alpha delta theta. This was the discussion we did in the last lecture. It's required to calculate the stress. So I want force over area. I will divide this with area. So the stress is negative E alpha delta theta. Substitute with the value of E given and the value of alpha and the value of delta theta. You will find the stress and you get it in Newton per meter square. What is the meaning of negative sign? Meaning that it's a compressive stress. This was an example on the thermal strain. Let's discuss some ideas about thermal strain. If in the problem I put the two rods in series like this is of material 1 and the second rod of material 2. How can I solve this problem? Delta L total between the two walls is 0. Between the two walls. Okay, from where I have delta L? I have it from rod number 1 plus rod number 2. Delta L total for rod number 1 is delta L thermal plus delta L mechanical. Similarly, for rod number 2, delta L thermal plus delta L mechanical. And remove every delta L and put it in terms of L alpha delta theta. Remove every delta L mechanical and put it FL over A. This is one of the ideas that we can discuss. Another idea, if the two rods 1 and 2 are parallel, not series, I am sure that delta L between the two walls is 0, which is applied for both, for 1 and for 2. So delta L total is 0, delta L1 is 0, delta L2 is 0. all are equal and all are equal to 0. Also note that in case of increase of temperature, when we are increasing the temperature, the delta L thermal is trying to increase, but I'm preventing it by the walls, so I have compressive stress. But if I'm decreasing temperature, if delta theta is decreasing, so delta L is trying to shrink, it's trying to decrease, shrink as if shrinking. But we are preventing it because we are putting it between two rigid walls. That's why, as if the walls are exerting tensile stress on the rod. The last idea we want to discuss with thermal strain, if I get the rod and put the two rigid walls, but I leave a gap, an empty space between the rod and the wall. So we have a gap, empty space between the rod and the second wall. What will happen? First, I will calculate delta L thermal. If delta L thermal is less than S, I will not reach the second wall, so no compressive stress. If it is equal to S exactly, I will just touch the second wall and no compressive force. If it's more than S, so this wall will prevent me from increasing in length, as if making compressive stress. As an example, if I calculate delta L thermal and I find it 3 millimeters, assume S is 5 millimeters, assume the gap is 5 millimeters, and I will calculate the delta L thermal. It is 3 millimeters. 3 milli is less than 5. I won't reach the wall yet, so no compressive force. If I calculate the delta L thermal and I find it 5 millimeters, it's equal to the gap width. I will just touch the wall and nothing will happen, so no compressive force. The case number 3, if delta L thermal is 7 millimeters, it's more than 5. So here we will have compressive force, but I will calculate delta L thermal dash, which is the difference, the 2 milli, and this is the delta L thermal dash, which is compensated with the delta L mechanical. Now we finish all the examples regarding the longitudinal elasticity. This is an example regarding the shear elasticity. Assume we have two metal plates connected with two bolts as shown in figure, and we apply this force and this force. These two forces, when acting on the bolt, are tangential to the cross-sectional area of the bolt. Take this part and magnify it as if the cross-sectional area of the bolt is being sheared with these two forces. It's given in this example the diameter of each bolt, the rigidity modulus of steel, and also the force acting on the plates. It's required to calculate the shearing stress. the shearing stress that develop in both or in each bolt. For one bolt, I will take only one bolt and I will imagine these two forces are shearing the bolt. So the stress is calculated by dividing the force with the tangential area. The tangential area here is an area of a circle, which is the cross-sectional area of the ball. Could be easily calculated pi over 4d squared, because here it's given the diameter of the ball. And I have to use the diameter in meter, not in centimeters. But I will take only half the force. Why half the force? Because this force is being equally distributed on these two bolts. This force is equally distributed and equally loaded on both bolts. So it's given that I will apply 20 kN. I will take only 10 kN and then divide by the area and then calculate the shear stress. The second required is to calculate the shear strain. We know that the shear stress equals the rigidity modulus multiplied by the shear strain. So the shear strain equals the shear stress divided by the rigidity modulus G. Calculated, and no units is needed because we are talking about strain, and strain has no units. The last example we want to discuss is an example on the bulk elasticity and how to deal with volume elasticity. In this example, we have a sphere of certain material. Its radius is 4 meters. It is designed so that the maximum elastic change in its radius under stress does not exceed 2 meters. 2 millimeters, I'm sorry. Find the maximum allowed depth of the sphere under the seawater given the density of seawater. This is the density of seawater and the bulk modulus of the material of the sphere, which is noted as K. Okay, let me explain what is this problem. We have this sphere. Its radius is 4 meters. I will put it under the water in depth H maximum. So it will be affected by change in pressure. If I have P naught, the atmospheric pressure acting on the surface of the water, and I want to get the pressure at depth H, it will be, I will name this point A. So I want to calculate the pressure at point A. It will be P naught plus rho of seawater, because I'm under seawater, G, gravitational acceleration, H maximum. This is what we know from calculating the pressure under the water surface. But what will affect the sphere? The increase in pressure, delta P. That's why I will use delta P rho water GH max. This will be pressure applied on the sphere, which will decrease its radius by 2 millimeters maximum. That's why we have equal stresses from all directions. We can use the law of volume stress and bulk elasticity. The volume stress equals bulk modulus multiplied by volume strain. As we explained in the lecture, the volume strain is delta V over V. And here we are dealing with pressure, not stress. So the pressure or the stress is negative the pressure. I want to calculate the delta P. So the delta P in the left-hand side equals negative K delta V over V. Instead of calculating the volume and the delta volume, I can use 3 double delta R over R. This is a rule, and I will explain it later now. So for a sphere, we can use triple delta R over R instead of delta V over V. Let's substitute negative K, 6 multiplies 10 to the power 9, 3 delta R over R. Delta R, it will shrink. That's why I put negative here, and I have another negative, it will be positive. Delta R over R. So increase in pressure is 9 multiplied 10 to the power 6. This increase in pressure equals rho C water multiplied G multiplied H max. I can get H maximum by dividing delta P over rho C water and G. You will find it 883 meters. So the maximum depth, I can put this sphere under it to make this delta R is this value. I will discuss this if you want to know from where is this rule. For a sphere, delta V over V equals delta R over R. You can memorize this rule. Because if you want to prove it, V equals volume of the sphere equals 4 over 3 pi R cubed. If you take len both sides, len V equal len the constant plus 3 len R, taking the len of the right hand side. Then take the derivative of both sides. Derivative of len is 1 over V dV equals derivative of this one is 0 plus R, or derivative of len R is 1 over R dr. So delta V over V equals 3 delta R over R. This could be used for the sphere. The same proof could be done for a cube. You will start with the volume of a cube equal A cubed. A cube has an edge equal edges. Its edge is A. You can make the same proof and you will prove that delta V over V equals triple delta A over A. This rule could be used for a sphere or a cube, but we have different rule for a cylinder, because for a cylinder we will not have the same. Thank you for listening.